Welcome to day 7. Yesterday, Euler's equation gave us Newton's second law for a fluid. But it completely ignored one thing, friction. Today's formula, the Navier-Stokes equation, puts friction back in. And it's arguably the single most important equation in all of fluid dynamics. So here is why it matters so much. So every CFT simulation and airspace company runs to design a real aircraft is underneath all the software, a computer solving this exact equation numerically, so millions of times over. So it's how engineers predict skin friction drag, boundary layers, and flow separation. So none of which Euler's equation can capture. A fun fact before we start, um, this equation is so difficult in its full form that proving smooth solutions always exist is literally one of the 7 millennium prize problem in mathematics. So with with a $1 million reward still unclaimed. So we are not solving that today. So but we will learn to use it. So here is the equation: rho times partial v partial t plus v dot grade v. So equals negative grade p plus mu grade squared v plus rho g. Don't panic. Look at what's familiar. So the left side and the last two terms on the right, negative grade p and rho g, are exactly Euler's equation from yesterday. There is only one new piece, mu grade squared v. That's a viscous force, right? So mu is mu is dynamic viscosity. So measured in Pascal seconds. So it's a property of the fluid itself. Air has a tiny viscosity, so about 1.8 times 10 to the minus 5 Pascal seconds. Honey, by contrast, has a viscosity thousands of times larger. So grade squared B measures how curved the velocity profile is. Essentially, how much neighboring layers of fluid are sliding against each other. Now, um, think of viscosity as internal stiffness. If you drag your hand through honey versus through air, you feel enormously more resistance in the honey. So that resistance is exactly what the mu grade squared V term represents mathematically. So there is a classic, fully solvable case that makes this concrete, called fat flow. So imagine two parallel plates with a thin layer of fluid between them. The bottom plate is fixed. The top plate moves at some velocity u, and the gap between them is h. In this setup, the viscous dam is the only thing balancing the motion, and the exact solution gives you a very clean result. The shear stress in the fluid equals mu times u over h. So this single friction dam is what actually creates the boundary layer over your wing. That thin sheet of slow down air right next to the surface. And it's the direct source of skin friction drag, one of the major drag components on any real aircraft. Let's calculate two things: the shear stress in a quad flow using a lubricating oil film, and a rough estimate of viscous force in an air boundary layer. The worked example in this slide: a thin film of lubricating oil, viscosity 0.5 pascals seconds, sits in a 2 millimeter gap between a fixed plate and a plate moving at 2 meters per second. To find the shear stress in the oil. So step one, use the quad flow formula. So F equals to mu times U over H. Step two, knowns. So mu is 0.5 Pascal seconds, U is 2 meters per second, H is 0.002 meters. Step three, substitute F equals 0.5 times 2 divided by 0.002. So step four, so calculate 0.5 times 2 is 1, and divide by 0.002, and you get 500 pascals. So the viscous shear stress in that thin oil film is 500 pascals. This is exactly the kind of calculation engineers do when designing lubrication systems and bearings. Now let's move for next worked example. So in this, near a wing surface, air velocity changes by 50 meters per second across a boundary layer just 1 millimeter thick. So air velocity is 1.8 times 10 to the minus 5 Pascal seconds. So estimate the viscous force per unit volume. Step 1, approximate the viscous time. Mu grade squared V is roughly mu times delta V divided by delta Y squared. So step 2, notes. Mu is 1.8 times 10 to the minus 5. So delta V is 50 meters per second. So delta Y is 0.001 meters. Step 3, substitute force equals 1.8 times 10 to the minus 5 times 50 divided by 0.001 square. So step 4, calculate 1.8 times 10 to the minus 5 times 50 is 9 times 10 to the minus 4. So divide by 0.001 square. So which is 10 to the minus 6. And you get 900 newtons per cubic meter. So even though air viscosity is tiny, fusing a large velocity change into a very thin layer produces a real significant viscous force. That's exactly why the boundary layer, even though it's thin, matters so much for drop. So mistakes to avoid now. So first, don't confuse dynamic viscosity mu with kinematic viscosity nu. So which you will meet on day 8. So they are related but not the same. And using the wrong one gives answers of by a factor of density. So second, the quad flow formula, tau equals mu u over h. So only applies to that specific symbol shear setup, a linear velocity profile with no pressure gradient. Don't apply it to arbitrary flows. Third, remember viscous effects matter most very close to a surface, in the boundary layer, far from any surface. Air behaves almost exactly like Euler's equation predicted on day 6. Now let's recap. The Navier-Stokes equation is Euler's equation plus 1 mu tau. So mu grade squared V, the viscous force. For simple shear flow between two plates, this simplifies beautifully to tau equals to mu u over h. So your practice question now. So an oil film with viscosity 0.8 Pascal seconds, a plate moving at 1.5 meter per second across a 1.5 millimeter gap. So find the shear stress. Drop your answers in the comments. That's a Navier-Stokes equation done. The equation behind every modern CFD simulation. So tomorrow, day 8, we finish the basic fluid dynamics category with the Reynolds number, the single number that tells you whether a flow will be smooth or turbulent. See you then.